Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Today we're going to be learning about a very interesting concept in physics that might be better known as the oomph of something. Oomph? That's like a physics term? Yeah, sort of. The term is momentum. And momentum is the oomph that something has. So when I have something that has high momentum, it resists change to movement. You've used the term momentum before, like a baseball team, like the Astros. They've got some momentum. That means it's hard to stop them from keeping winning. So it's really defined as the resistance to changing movement. Now think about this. I'm sure you've thought this through, and you know this. What variables make something hard to stop moving? So let's say a baseball flies across the screen. What characteristics are going to make that difficult for you to stop it moving? Now one of them, if you think about it, if it's a heavy object, it's harder to stop a heavy object moving than a lighter object. So mass plays a role. But what else? It's also harder to stop an object that's moving faster. So velocity plays a role. Turns out that momentum is the interplay, if you will, of mass and velocity. In fact, it's mass times velocity, and we call this P. Now, I don't know why we call this P. The symbol for momentum is P. You can't use M because M is mass. I don't know. V for momentum. I don't know. Velocity. By the way, this is important. This is a vector because velocity is a vector. So momentum also has directions. And so sometimes you can have the angles and the whole SOHCAHTOA thing going on, and we're going to do that. But this is the essence of what momentum is. Now, when you think about momentum, you might say, don't we already have something we've learned about that deals with mass and velocity? You might recall this equation. Kinetic energy is 1/2 mv squared. So if you got m and v twice, mv, what's the difference? First of all, this is a vector. So let's do a compare and contrast. This is a vector, this is a scalar. Now, recall, vector means you can play the whole angle game. A scalar is just a number, so it has so many joules of energy. So energy and momentum are kind of related, but they're not the same thing. Something else we're going to learn about, we haven't learned about this, momentum is conserved. I mean, the total momentum in equals the total momentum out. Kinetic energy is not conserved. Actually, we'll say not usually conserved. There's an example where that does happen in our last video. We'll get to that. So there's some differences between these that make a difference. And one of the things we should talk about momentum is what's the units on momentum. Now, it doesn't have the energy on the unit on this is a joule, right? But if you think about that, this is a kilogram, meter per second times meter per second. So kilogram meter squared per second squared. But this is going to be a kilogram meter per second. That's it. And we don't have any fancy unit. We don't call it a joule or a Bergmann. We don't call it any of that stuff. We just call it a kilogram meter per second. It's the unit for momentum. So let's look at this table here and do like a sample problem, really simple sample problem. So let's rank these in terms of their resistance to change in movement or their momentum. So the first one, if you see, it's 10 kilograms, I've got it on the paper here, and 10 meters per second. So that's going to be 100 kilogram meter per second. The second one, we're going to be 15 times 4, so that's 60. I'm going to have to put the units there just to make it easier. And the third one is going to be 100, right? Because it's going to be 5 times 20. And then letter D is going to be 180. So if you know this, you can put these in order. This would be number 1, number 2, tie ball game here. And this is number 4 from as we rank them. Now let's talk about an interesting question in terms of momentum. So the second problem on the notes outline sheet is, so let's say we've got a meatball, all right? A 1 kilogram meatball, and it's moving at 1,000 meters per second. And secondarily, we've got a truck, all right? Big old truck. All right, doesn't look like a truck. That's a car. Whatever. And let's say that it weighs 1,000 kilograms, but it's moving at 1 meter per second. Now what I want to do is I want to contrast a couple things that we were talking about a minute. So let's figure out the momentum. Remember, momentum P is equal to mv, so this will be m1 times 1,000, which is 1,000. Got it? That's 1,000 kilogram meter per second. So the momentum of this is this, right? What is the momentum of the truck? We would say 1,000 kilograms times 1 meter per second, which is 1,000 kilograms meter per second. So they have the same momentum. But let's ask the more interesting question. Which would you rather get hit by? Now, so you're standing in front of this and standing in front of this. Probably the answer would be the same, right? Which one would actually kill you? Would a truck moving 1 meter per second, hurt you more than this? You see, because this is where we take into consideration the kinetic energy, because the kinetic energies aren't the same. What's the kinetic energy equation, right? 1/2 mv squared. So let's apply that. If this is 1/2 mv squared, I say 1/2 times m times 1 times 1,000 squared. And this will be 1,000, or 1/2, times 1,000 times 1 squared. So that's just going to be 500. And that's joules, right? Now this is going to be 1,000 squared. 1,000 squared is 1,000,000. So this will be 500,000 joules. Essentially what you have, I know it's a cheesy meatball, the amount of energy that'll be imparted into your body is 500,000 joules versus 500. This is a bullet. This will kill you. Let's do one more problem. This is the duck-goose problem. So I've got a duck. I don't know, it looks like a duck. We got 2 ducks. Okay, don't judge me, okay? And we've got a goose. Gooses are bigger. Okay, and don't judge me. All right, both of these ducks weigh 4 kilograms, right? The goose weighs 7.6 kilograms. They're moving in opposite directions. This is important. These cats are moving at 1.1 meters per second. I guess they're not cats. These ducks. And this cat is moving at 1.3 meters per second. So what happens when they come together at the bred, right? So it's going to be pretty simple here. We've got 4, we can treat these guys as 1, so that's 8 kilograms times 1.1 meters per second. So 8 times 1.1. Their momentum is 8.8. I guess I could have done that in my head. And these guys' momentum in the opposite direction, so that's in the positive x direction, is 7.6 times 1.3. And this is 9.88. Now what's going to happen is these guys are kind of going to see that collision thing we talked about a minute ago, is when they collide, his momentum is going to push this back. So the net momentum is going to be the difference between the two. So 9.8 minus 1.8 is 1 kilogram meter per second. And what's going to happen is that then their velocity is going to be going backward in this direction. But we can now set this up to our new mv, because when they become together, their total mass will be 8 plus 7.6. 8 and 7 is 15.6, so that's equal to 15.6 v equals 1. So I divide both sides by 15.6. And I get 0.064 meters per second. Now this will be negative because this goose is going to push back the ducks, and so the final velocity, because it has, it is a vector, and we're just working in the x direction, the positive x direction, will be negative 0.064 meters per second. Folks, momentum, it's not super hard. M times v, you can mv, and you're like mv equals mv. You're going to solve these problems super easy. It really has a lot to do with how things collide, and we're going to get to there a little bit later. Houston, we got no problem.